Hello everyone, welcome to Easy Physics again. Now we are going to learn total internal reflection. From our previous lessons, we know that when light attempts to move from a medium of high index refraction to a medium of low index refraction, for example, from water to air. Let's draw a normal. When light rays are moving from high index of refraction to a low index of refraction, what happens? Assume this is our incident ray. Now it is going to move from water to air. We know that when it is moving from high index of refraction to low index of refraction, it bends away from the normal. This is the angle of incidence and this is the angle of refraction. There is a relationship between these two angles. As we increase this angle, this is also going to increase. It is a consequences of the Snell's law. This phenomena has some other results. Assume now we have a light source here inside water, or inside an index of refraction n is equal index of refraction n1 and another index of refraction, another medium of index of refraction n2, and assume that n1 is bigger than n2. Now, light from this source will spread to all of the directions. For sake of simplicity, let's look at several light rays emerging from this source. Look at this one on the left. It is moving straight upward and it passes to the second medium without undergoing any refractions. Let's look at this one. As you see, this one is moving from high index of refraction to a low index of refraction, and it bends away from the normal. Let's draw another one. For example, this one. This light ray is also going to refract, but it will refract more than this one. Why? As I explained here, there is a relationship between these two angles. As you increase this angle also increases. Now look at this light ray from the same source. As you see, as we increase the angle of incidence, here the angle of incidence is 0, here we have some angle of incidence, here we have another angle of incidence. This is the normal. We have another angle of incidence, and at a critical angle, the angle of refraction becomes 90 degrees and the light moves along the interface between the two mediums. And at this angle, where the angle of refraction is 90 degrees, the angle of incidence is called critical angle. Okay, but this is not all. When the angle of incidence is bigger than the critical angle, something interesting happens, and the light ray, is reflecting with the same angle. Up to here, we have some refractions. This is the normal. It refracts. Here, it also refracts. Here, also refracts. But when the incident ray has an angle bigger than the critical angle, it reflects back into the same medium. What is important here that you need to remember is that this total internal reflection phenomena happens when the light attempts to move from high index of refraction to low index of refraction. Okay, we know that the Snell's law is expressed as n1 sine theta 1 equals n2 sine theta 2. Let's find an equation for the critical angle. Let's apply the Snell's law to this condition. When the incident angle is equal to angle of incidence is equal to critical angle, n1 sine theta critical equals n2 sine 90 degrees, because when the angle of incidence is equal to critical angle, the refracted light has an angle of refraction 90 degrees. We know that sine 90 is equal to 1. So from here, we can write that sine theta critical equal n2 divided by n1. Okay, we can now use this total internal reflection to solve some problems. Let's look at the first one. Here we have a light source. The light is emerging from this source to all directions, and here we have shown 1, 2, 3, 4, 5, and here we have shown the ray. It is called S, and it is undergoing it is moving with critical angle. This angle is angle of incidence, it is moving with the critical angle. Why? Because as you see, the angle of refraction is equal to 90 degrees. So here it asks which ray from point O will undergo total internal reflection. When the total internal reflection occurs, when the incident angle is bigger than the critical angle. Now, what is the critical angle in this case? As you see, the critical angle here is equal to 45 degrees. Why? Because here we have 1, 2, 3 units, and here we also have 1, 2, 3 units. So this makes 45 degrees here. So can this one undergo total internal reflection? No, this is a straight line, straight light ray. It will pass to the other surface, other medium, without any refraction. This is going to refract. This is also going to refract. The one which is moving with the 45 degree is equal to this one. It will move along the interface between the two mediums. Why? Because this is 45 degree. Again, 1, 2, 3 units, and 1, 2, 3 units. Now this light ray, the fifth one, has an angle bigger than the critical angle. That's why this one will undergo a total internal reflection. The correct answer is this one. Next question. Which of the following cannot be a refracted or reflected ray? The light is attempting to pass from medium X to medium Y. Now, depending on the index of refraction of these two mediums, the incident light ray can go straight without changing its direction. If nx is equal to ny, it will move like this without changing any direction. This is possible if nx is equal to ny. What about the sixth one? Any light ray after refraction can move toward the normal, and the angle of refraction will have some values, but none of the incident light ray can move straight downward. I mean, the angle of refraction cannot be zero. If the light is moving downward like this, it means that it will move along the normal, and angle of refraction will be equal to 0, and this is impossible. If nx is bigger than ny, in this case, if nx is bigger, then the light can refract like this. It can move away from the normal. It also can move with the critical angle. This can be all the angle. It's also possible. Then, if the angle of incidence, assume if it is bigger than the critical angle, it will reflect with the same angle. This is also possible, but the second one cannot be possible. Why? Because this angle is different from the angle of incidence. For the total internal reflection, the angle of incidence should be angle of reflection. So the answer is sixth one is impossible, and the second one is impossible. Let's look at the third question. Here light is moving in medium X, and then it is trying to move to the medium Y, but this is the original direction of the light. It was moving in this direction, but as you see, it has bended this much, and now it is moving between the interface between the two surfaces. Here it was moving in this direction again with the same direction. This was the original direction, but now it has bended more. So remember, the light is bending away from the normal when it is attempting to move from high index of refraction to low index of refraction. In both cases, nx is bigger than ny, and nx is bigger than nz. But what is the relationship between the y and z? The amount of refraction here and here is more in z. What does this mean? As much as the index of refractions are different, that much amount of refraction increases. I mean, for example, if the index of refraction, this one is 3, and index of refraction of this one, for example, 2, and index of refraction of this one is equal to 1. The difference between these two index of refraction is 3 and 2. It is the difference is equal to 1. The difference between these two index of refraction will be 2. 3 minus 1 will be equal to 2. So let me repeat, as much as the difference between the index of refractions, that much amount of bending occur. So here we have more refraction. Here we have more refraction when compared to the refraction here. It means nz is much more smaller than nx. So nx will be bigger than ny, and it will be bigger than nz. Let's look at the next question. Here we have a prism, 60 degree, 90 degree. Here will be 30 degrees. And now we are asked which light ray will undergo total internal reflection. And the critical angle for prism air boundary is 30 degree. If the incident light ray has an angle of incidence more than 30, then the light will undergo total internal reflection. Let's look at K. This light ray will move straight up to here. Why? Because it is entering from air to the prism with 90 degrees, it will not bend. Now, when the light comes here, is it going to pass to the air, or is it going to move? It will undergo a total internal reflection. Let's look at the angle of incidence. First, let's draw a normal. So this is the normal. It is an angle. It is a line perpendicular to the surface. Now let's look at the angle of incidence. I mean this angle. Here is 30 degree. This is 90 degree. This one will be 60 degrees. And this angle will be 30 degree. And the angle of incidence is exactly the critical angle. That's why the light is going to move along the interface. So no total internal reflection will occur. Let's look at L. Let me draw the prism here. Okay, let's use another color. And the light ray is now moving from air to the prism with 90 degree. This angle is 90 degree. And when the light ray, this light ray, when it comes to this boundary, is it going to move to the air, or is it undergo some internal reflections? Let's again draw the normal here. This is the normal, and we know that this angle is 30 degrees, this is 90 degree, and this will be 60 degree, and this is going to be equal to 30 degrees. As you see, the angle of incidence, the angle which is the angle between the incident ray and the normal, is equal to 30 degree. That's why this light ray will move along the boundary between the two surfaces. No total internal reflection occur here also. Let's look at the next one. Let me draw the prism again. Okay, so let's use another color. Here the M is moving straight upward. It will move like this. This is 90 degree. Let's look at the angle here with the normal. Let's first draw our normal. This is the normal. And we know that this angle is 90 degree. This angle is 60 degrees. This angle will be 30 degree. But this angle will be 60 degrees. As you see, angle of incidence, angle with the incident ray and normal, is bigger than the critical angle, so it will reflect with the same angle. So let's use this one, and it will reflect with the same angle with the 60 degrees. So this light ray, 60 degree, this light ray will undergo total internal reflection at this surface. Let's solve our last example. A small light bulb is set in the bottom of a 3-meter deep swimming pool. What is the diameter of the circle of light seen on the water surface from above? Now assume this is the boundary between the water and the air. This is the bottom of the swimming pool. Assume we have a light source here, and the width or the depth of the swimming pool is given 3 meters. So light from here will move to every direction. For example, a straight light ray will move straightly and it will pass to the air without any refraction. Another light ray will move to that direction and it will bend away from the normal. I am not going to draw the normal, but at a critical angle the light ray will reflect at a critical angle the light ray will move along the interface. At the critical angle it will move along the interface. So this is the 90 degrees. Okay, here is the critical angle. Any other light ray bigger than this one will reflect downward. It will not emerge to the air, so it will not illuminate the surface of the water. Only light rays which have smaller angle of incidence, which has angle of incidence smaller than critical angle, they will pass to the air. Others will reflect back into the water. How can we calculate the radius of the area which is going to be illuminated? To calculate the radius of the area which is going to be illuminated, let's use the Snell's law. We know that n1 sine theta 1 equals n2 sine theta 2. Okay, assume this is n1 and this is n2. We know that n1 is water and n2 is air, and index of refraction of water is 4/3 times sine theta critical. I am using Snell's law for this point, equals n air is equal to 1 times sine 90. Why? Because at this moment the angle of refraction is 90 degrees. Sine 90 is equal to 1. So from here the sine theta critical will be equal to 3/4. Okay, so let's calculate the diameter. This is r from here to here. This is the diameter of the area which is going to be seen from the above as illuminated. This is r, and this height is 3 meters. How can we find r? We can use tangent theta critical will be equal to the tangent of this angle will be equal to r/3. We know the sine of the critical angle, but we don't know the tangent of the critical angle. Let's draw a triangle. This is theta critical. The sine of this angle is equal to 3/4. So can we find this length? Yes. Let's call it x. From the rules of trigonometry, we can write x squared plus 3 squared equals 4 squared. Then x squared is equal to 16 minus 9. Then from here x will be equal to square root of 7. Now we can write the tangent. The tangent of theta critical is 3/x, but x we found square root of 7. This will be equal to tangent of theta critical is going to be 3/square root of 7. So from here r will be equal to 9/square root of 7. If you calculate it, approximately it will be 3.4 meters. So light is, let's move back to our question. Light from this source will move from here to the air, from here to the air, from here to the air again. But at critical angle, assume this is the critical angle, light is going to run between the interface. Any light ray bigger than the critical angle will reflect back. All other light rays will reflect back, which are bigger than the critical angle. So an area here on the surface of the water will be illuminated, and its radius will be equal to r equal 3.4 meters. That's all. Thank you for listening.